Okay, everyone. So before I introduce Michael, I just wanted to remind everyone that we have the holiday party immediately after. Food and drink and so on is I think, mostly up on the 10th floor. So today we're very happy to have Michael Douglas. So he's a theoretical physicist and a mathematician. Did his PhD at Caltech. And you told me an interesting story this morning that when you went to Caltech because of some work on neural networks, but realized when you got there that its time had not yet come, whereas string theory was actually in an extremely exciting phase. And that was when anomaly cancellation was discovered, in part by John Schwartz. So if you've heard of the book Green, Schwartz, and Witten, that's the Schwartz. So Michael did his PhD under John Schwartz, moved to Rutgers. And another interesting connection to NYU is that at Rutgers there was this string quartet. There was a center for theoretical physics, which was, I don't know exactly the first of its kind, but one of the first of these centers within departments. It was very successful and served as a model for the centers that we have in the physics department today. In fact, Glennis was at Rutgers, moved here, and sort of imported that idea of centers to NYU. It's been a very successful model. Anyway, so Michael remained at Rutgers, was the director of the center for some time, moved to the Simon Center for was it called geometry and physics? At Stonybrook University, and from there to Renaissance Capital, where he's been working for some years, but maintaining his connections to academia and continuing to do really interesting work. He's the recipient of numerous awards and prizes, the Sackler Prize. He's a fellow of the American Mathematical Society, and he's going to tell us about the future, which is always a very brave thing to be doing. So let's all welcome Michael.
Thank you for the generous introduction. It's always a great pleasure to visit NYU. You have a great group in cosmology and particle physics and many other things. So I'm going to survey this area of mathematics and computation, and it's been fun. I've been spending part of the last few months visiting many leading researchers doing things like this, and partly tell you some cutting edge things, and partly really trying to take stock of what we have now and figure out where are things going to go. And so as part of doing that, one should give some sort of a historical background. And by the way, when I say mathematics in this talk, I mean it in the broad sense of the mathematical sciences, all these fields where we use mathematics or mathematical concepts, but perhaps for their own sake, or perhaps to understand the world we live in. And I do think that we've clearly seen many changes thanks to computers and other forms of technology, and that this is really going to accelerate in our fields in the coming decade. Okay, so to start, to take the long view, we can give a kind of very condensed history of computer science. And of course, as you know, computers date back 60, 70 years. The concept's not that much longer. And originally, they were big calculators. They were built to do numerical calculations, weather forecasting, tables for artillery or for designing bombs. But in the 50s, various pioneers of computer science saw that these were really very general purpose devices that you could use to store and search for and retrieve information, that you could build control systems with digital logic as the fundamental component. You could even try to reproduce the human reasoning abilities or other natural reasoning and computing systems. And of course, I could give an equally long or longer talk about just the already existing contributions just within this vein of all the computational results, discoveries, and I'll touch on a few of them later. So this field of AI goes back to the very early days, Newell and Simon, the 50s. And people tried, as one of the very first papers in this topic was developed something they called the Theorem prover, which tried to to prove statements in Boolean logic. And they were just starting, and they just basically searched through all the possibilities. And as many of you will know, that type of naive search runs into the barrier of exponential time and cannot get very far. But the foundations, a lot of the dreams were set out at that time. So skipping forward in the especially late 80s, early 90s was the dawn, or at least the public dawn of the internet. And this has already had a big impact in how we do research. And I like to tell a story from my own field of string theory, that when I went to Caltech studying with John Schwartz, it was a little frustrating because it was a very exciting time with a lot of discoveries, but by far most of the discoveries were being made in Princeton and the Institute and a few at Harvard and so forth. And what would happen is we would learn about them by preprints. We would get this big box in the mail of preprints. And we would eagerly open and read and come up with ideas and conjectures and things to work on and start working. And then we would get someplace. Here's a good problem. And then the next box would come, and of course our problems would already have been solved. And then the preprints coming out of that box. And so it was frustrating. But in the 90s is a period that we call the second superstring revolution. And this was really, you can trace back to the beginning, this duality revolution. This idea of a duality was taken seriously by Ashok Sen in India. And he was able to find arguments that convince people that this old crazy idea really had something to it. You could write papers that you could check were right or wrong. And so when our group at Rutgers, many people picked this up. But the difference was that now we had the archive. So in '91, Paul Ginsberg had taken over this mailing list that postdoc Joanne Cohen had started. It was mailing, first emailing, and then on the web, had a web page with the preprints. And so anybody working anywhere now could get the same access to the preprints. And the second revolution was a much more distributed phenomenon. It happened around the world. And so there's a very concrete example. And I think if you search the landscape for examples, I think the one arguably the greatest success story of this type of collaboration facilitated by the internet is Wikipedia. And when Wikipedia was first set out, 2000s, a lot of people thought this would not work, and told me that. And just basically, people outside Wikipedia is an old idea and always required a group of editors and a lot of organization. So the idea that just you could let people type stuff into this was crazy. But of course, it worked much better. It's hardly a perfect thing. It hardly replaces curated, repositories of knowledge, but it works surprisingly well. So now we're in this third phase of machine learning. Okay, skipping forward again, and this is the subject of newspaper articles, and especially a place like NYU, which is quite active in this. You will have seen many of these discoveries, and of course, it's already become core technology for technology firms like Google, Apple, Facebook, who fired thousands of researchers, likely including grad students, postdocs from here, and certainly from Stonybrook and other universities I'm familiar with. And so very active thing. And the question now, for purposes of this talk, will be, can we now use it to help us do our research, or to communicate our research, or to teach? Now, of course, it is a mathematical concept itself, machine learning. We could make a talk and write down the equations describing a deep neural network and so forth, but we're going to turn that around here and instead grant that that's a technology that exists. How can we use it to help do mathematical science? Okay, so again, in this vein of setting the backdrop, to be able to better extrapolate, let's survey what's out there. And many people will be familiar with many of the terms and systems and so forth on this list. And if you're not, these are all things you can easily look up in Google, and it's worth looking up and finding out what they are. And this slide is in the category of media and tools, things that help us make documents, communicate with each other, but not so specific to mathematics. But we certainly do use them. So obviously, LaTeX, very important. Hypertext as a medium, the archive I mentioned, various other authoring tools to write web pages. MathML is a standard for representing mathematical notation that's standardized. Of course, many people here will use Mathematica, which I'll come back to, but a secondary innovation of Mathematica and Wilfram research was this notebook format, which is very convenient for assembling coherent series of results. Search, social media is an interesting thing. Things like Stack Overflow can be especially helpful for students, but helpful for all of us in getting questions answered. I'll move on now to computational tools, so more really specifically for math, physics, and mathematical sciences. And of course, the top of the list would be symbolic algebra. So again, one of these fairly early outgrowths of AI. The early systems were written in Lisp, which was developed to do AI, and these gradually evolved into the systems we have now. Mathematica, SageMath is probably the leading open source system compared to Mathematica, if you will. There are a lot of specialized systems which were developed by groups of mathematicians to solve group theory or algebraic geometry, the specific problems in their discipline. And all the open source ones, I think in this list all but of Magma, have also been incorporated into the SageMath. So being open source means that you can incorporate and make a lot of things work together. There's an interesting list of maybe 30 or 40 of these that have seen a fair amount of use. Software development tools is a bit outside of, so as a physicist, unless you really develop software, or unless you're, I'll just say under 30 to pull a number out of the hat, you may not have ever used these, but software developers and I find people that are learning computing now tend to be very familiar both with languages like Python and especially systems like GitHub that are version controlled that let you keep track of the many versions of a document or a piece of software, and save a lot of trouble doing that. And those are things we can learn from. They're not specific to the mathematical sciences, but they are technologies of use to us that you can imagine extrapolating from to imagine what's possible. Okay, mathematical databases. So a famous example of this is the online encyclopedia of integer sequences of Neil Sloan collaborator. So you can have a series, 1, 1, 2, 3, 5, 8, and type it in, and it will tell you, yes, that's the beginning of the Fibonacci numbers. Maybe it also begins other sequences, and so that can be a useful tool in practical research. And there are various mathematical databases of popular enough constructions. There's a survey of these at this link that one can look at. I'm going to come back to this in quite a bit more detail. Interactive theorem verification. So this is systems where you can construct a proof, a real mathematical, and not just rigorous, but sort of hyper-rigorous formal proof in the style that you might imagine Russell and Whitehead would have done if they'd had the technology. They famously proved that 1 + 1 = 2 in something like 50 pages. And now you can do it in less than a page if you start from ZFC. But in any case, these systems are very interesting and have their uses, and I'll come back to this topic. A few more experimental things again, I'll come back to a few of these. Okay, so the idea of a collaborative textbook. There's this famous Stacks project in algebraic geometry that you can look at. I'll talk about mathematical search at some length shortly. There's what's called the polymath collaboration. So using, not so much social media, but just the ability to work together easily bring together large groups of people to work on the same problem. This polymath collaboration has proven interesting results, such as the distribution of primes separated by an interval. I'll come back to this AI and theorem proving topic in some detail. And let's move on. Okay, so mathematical search. Okay, so again, some of these technologies everybody will at least heard of, and some of you use a lot. Everybody here probably has used LaTeX. Everybody here probably looks at archive. Many people probably use Mathematica. But now let's move on to the things that you don't use so much because they don't really work or they don't really exist. And so search, mathematical search. So for example, Tim Gowers, a field novelist, has emphasized the value of a mathematical search engine. Okay, well, it's what you might think it is. You describe a mathematical concept and it defines all the publicly available, all the stuff on the web which is related to that concept. And you might say, well, I do that all the time. And you do it, and if you know the name of the thing you're looking for, the existing technology, Google and the rest, works very well. And so if I know that I learned what a subless space was in some math course, and now I have to refresh my memory as to the definitions, I can type subless space. And I will get quite a bit of information, both because the search engine works and because people have log documents and Wikipedia and many places that this can link to. Okay, so that's very good. But what if we don't know the name? What if we didn't learn that in our math classes? What if it's a much more obscure concept? That only a small fraction of people know about. What if we invent a new mathematical concept to prove a new theorem? Okay, well, what's the name? Who knows what the name is? Probably, it's of course quite likely. As good scholars, we would all do the literature search and try to find out, did somebody invent this before? Maybe they actually have something useful for me, or at the very least I should reference them. But you don't know the name because they invented it, so how do you search for that? And well, in general, that would be a very hard question to answer. But in math, we can at least imagine an answer because we can define precisely the things that we're talking about. They all have, by definition of mathematics, they have precise definitions. So we can type in something about the definition and try to search based on that. And so we could try to type in a formula. And in fact, there are a couple of attempts online to do this. There's a site, www.searchonmath.com, that some people in Brazil have developed that searches the Stack Overflow and a few other archives. So I tried it out when I was preparing this talk, and I asked, well, suppose I had the definition of prime numbers, okay, just as a test, okay. So you type in a kind of a LaTeX-like form there, and then it puts it out in the LaTeX output. And this is, of course, if you think about it, not quite right. So we're asking for the set of P such that there's no n greater than 1 that divides P. And if you think about it, you realize, well, P, I should also say it's not P, but pretty close, okay? And I typed that in, and this was the first result I got. By definition, how is a prime number represented? So that was pretty good. Okay, so then I will try a harder one. Okay, I will try f is in the space of L2 functions on R, and this derivative is in the space of L2 functions on R. And then I got this as the first answer. And it's not quite as good because it's not literally the definition, but it does talk about the right concept. It's got that word sublef in it. So definitely this is something to build on. So I would count that as a success too. So maybe the formula-based thing is already pretty good. And again, you can try this website yourself. But it's not as good as those examples, okay? And so another test was that the letter P in my first query is usually often used to represent a prime number. So what if we had switched it to a Q? So in this query, I fixed my bug. So this is actually a correct query where the other one was not, but I used that letter Q instead of P, and that totally fooled it. Now it doesn't have no clue that it had to do with prime number. So it's not really the answer. Now there is a better one that does. So what was the solution to the problem I just said? You could type something like a question mark P, which would mean I want to use a variable. Every time I refer to it in my query, it would be question mark P, but it could match any variable name, right? So it'd be anonymized in that sense, or unbound. And then there is a search engine, Michael Kohlhaas's group. This is the one that's used in ZB Math. This is like the German analog of the mathematical reviews. But I must admit it doesn't work that much better on the things I tried. But in any case, one can fix individual problems. Now let me get into some deeper problems with this. And well, you know, obviously, you know, I chose cases where it was pretty obvious what the formula would be. And often it's not as obvious what the formula should be either because, well, it could be an extremely long formula because you can get anything up out of primitive definitions with a long enough formula, but then it's going to be hard to type and hard to find. Or, of course, you could use existing definitions. So I could be looking for the concept of a simple group, so it has no non-trivial normal subgroups. And so if I'm allowed to use the concept normal, that's a one-liner. But how do I know how to say normal? Right? Or should I say H is a normal subgroup of G is normal HG, or maybe it should be normal GH? I mean, if you look at a group theory textbook, they're both not what they use. They have this kind of triangle on its side. H is a normal subgroup of G. So how am I supposed to know that? So anyways, there are all these issues that start to come, you know, that come up, which are like things that one deals with in dealing with computers and start to stand in the way. Okay, so perhaps part of the search engine is to be more systematic about definitions and libraries. And I'm actually going to come back to that topic later in the talk. Let's suppose we get past these questions. Okay, well, now we found a relevant definition, maybe even a relevant program, you know, to do something of value for us. List the prime numbers, you know, or find. I gave the solutions, you know, representing an integer as the sum of 4 squares in a longer version of this talk. And then what? Okay, well, another issue, which, you know, is always there in search, but it really becomes very precise in the context of mathematics, is how do we know that things we found are correct? You know, what do we do? Well, we could always take search results as hints. We could say, well, now that's a good idea. I'm going to now rederive it for myself, which is what they, you know, what we tell our students to do in grad school, which is a good thing if you're a grad student, but you know, you eventually have to teach and you have kids and you don't have time. And then the other extreme, of course, would be it's on the web. Let's just believe it. You know, see if it works. And you know, although, you know, in some moral sense one might be better, of course, 2 is often the correct thing to do. It is a correct result, and you should use it. Okay, and so now this question of how do we know if search results are correct is also kind of important in this. And I'm going to come back to the theorem verification, but again, just to kind of lay out possibilities. Okay, so there are, you know, many libraries curated in the sense that they list, here are routines, somebody has gone through and checked. They at least are saying that those routines work for their purpose. That has its value, but of course you cannot then search for arbitrary content on the web. You may want a way to make it easy to check things by example, or you may insist that there really be a proof of the thing. Okay, so all these are, you know, kind of setting out this landscape of mathematical search and how you would actually use it. That if you then think and say, well, you know, maybe in 10 years there will be tools or ways to do all these things for us in, you know, much more standardized and useful ways. Okay, so now let me switch, having gone, you know, to some depth in mathematical search, this broader topic of really directly using the computational power to look at mathematical concepts and results to inspire our mathematics and physics. And of course, many discoveries have already been, you know, heavily based on this sort of approach. So the whole theory of dynamical systems, a lot of it was inspired by the result of computer simulation. The people that classified the finite simple groups made heavy use of computer constructions and representations of groups. The famous Birch-Swinnerton-Dyer conjecture, one of the 7 millennial problems of the Clay Institute, is actually based on computer calculations of properties of elliptic curves back in the 50s and 60s. And this tradition certainly goes on. There's an active collaboration funded by the Simons Foundation in that very topic. So, okay, so that's an extent, you know, again, you know, the well-established, you know, computational mathematics. And how will that evolve over the coming decade? Well, the easiest thing to predict, of course, is that we'll have faster computers, cheaper computers. It's true Moore's law in some sense may have saturated, but we still are getting speed ups by parallelism, by other technologies. Computers are getting cheaper. And if we make a kind of a rough extrapolation of Moore's law, it's a fair statement that if these techniques were within a factor of 1,000 of time or space of solving a problem now, then it'll probably be solved that way in the coming decades. So that's like an easy prediction to make, but a non-trivial one. Okay, here's another technology of this theorem proving type, which is to deal with proofs when you're just talking about sets of Boolean or logical propositions. And so an example of a famous, or not incredibly, but famous enough problem, which was recently solved this way, is what's called the Boolean Pythagorean triple problem. Okay, so we have the set of positive integers from 1 to n, and the question is, can you split them into two sets, say red and blue, such that neither set within itself contains a Pythagorean triple, a squared plus b squared equals c squared. And so by computer search, this group, Hoyle et al., found such a solution for 7824 and proved that there is no such solution for 7825. And in fact, the computer proof of this statement is 200 terabytes long. So in some sense, it's the world's longest proof, at least for now.
Just for curiosity,
Yeah.
it's the integers up to that end?
Yeah, that's right.
It's
the
not,
whole
you're not
set.
skipping. Oh,
We're
okay.
not skipping, that's right. And okay, so how did they do this? Okay, well, this is using a SAT solver, which is something that you take a list of Boolean clauses. So Boolean true/false variables can be combined using and, or, and not. And there might be specific rules, but already that's a universal thing. So if you can easily phrase your problem in those terms, there are industrial strength SAT solvers which can solve systems with millions of these clauses, tens of thousands of variables. It's used in chip design and other things. And so here it's pretty clear. You would say for each of the integers, there's a variable which says, is it in set A or is it in set B? And then you translate all of these conditions into clauses saying that if there exists, I want to enforce each statement that each choice of A, B, C within a given set doesn't appear all within the same set. So that's just a finite list, which is easy to generate, and you feed it to this SAT solver. Okay, so again, a very kind of a specialized problem, but then there are groups, and in particular there's a group at the Waterloo that I'll talk about momentarily. So this was a very simple case because the actual clauses are so easy to list and evaluate. Often you have some complicated equation, some complicated combinatorial optimization or satisfaction problem where you don't want to evaluate the equations unless you absolutely have to. And then you would make a sort of a combined system with a computer algebra system and a SAT solver, where the computer algebra system evaluates the clauses on a need-to-know basis. Once the logic realizes, yes, I have to know if that's true or false, then it evaluates. And a few examples of problems that have been done that way. So the Williamson conjecture, this came out of statistics actually. So find 4 symmetric n by n matrices, all of whose entries are plus and minus 1s, such that the sum of their squares is proportional to the identity matrix. So this comes up in the problem of experimental design and statistics. And so it's been shown by this group at Waterloo that these exist for all n up to 35. It does not exist for n equals 35. So the original conjecture, of course, was that it always existed based on the low cases, but that's falsified. And it exists for all the even n up to 70. So it's kind of crazy. There is no standard conjecture as to what the actual existence condition is. This is another problem, and another kind of famous problem in computer science is this problem of what's the minimal number of multiplications you need to multiply two matrices. So if you take like two 2x2 matrices, if you just do it the obvious way, you'll multiply 8 times. But you can show that you actually can do it if you multiply them 7 times by regrouping. You're doing sums and differences, then doing the multiplications, and then doing sums and differences. You can multiply using 7. And so in fact, you can show that as the matrix size becomes large, the power of the exponent of the difficulty is less than 3 because of that. And so anyways, now there's this open question. Well, people proved that you need 7 for 2x2, but what about 3x3? And you can do it using 23, and these people list a vast number of 10,000 different ways of doing it with 23. No ways with 22, but no proof as yet. So these slightly intricate combinatorial problems are well suited to this approach, and sometimes they are, very important problems. Okay, so neural networks. No talk on this topic would be complete without mentioning neural networks, and I'm just going to keep it to the minimum because this again could be a whole talk in itself. So an area of interesting application for the mathematical sciences, even leaving aside machine learning and the rest, is function fitting. We represent a lot of functions, especially in numerical work, and all these problems, optimization, TDE, quantum mechanics, very interesting to have other ansatz besides the ones that have been developed. The neural network ansatz often seem to be better than the ones people have been using for decades, and there's very interesting theoretical questions that this raises as well. So this obviously is a trend that will continue to be important and develop. Another trend I would say I see when I read the math literature, try to solve my problems, is that people think more in statistical terms, even in pure mathematics. Of course, physicists, we've always had to think in statistical terms, but the foundations of statistics, I mean, maybe me as a physicist, coming at it from the outside, but I do think it is becoming more sophisticated and more based on generally applicable concepts, so that in particular, because you have a bigger computer, you don't necessarily need to optimize for the specific problem at hand. You can use a general concept to try to address your problem, and there are many sources of them in statistics. I'm going to come back to this one about the Wasserstein distance and mention it's just one of a large number of examples. I could talk about examples developed here, but this is one developed at MIT by Jesse Taylor's group. And so in analyzing collider events, the question, what you deal with, how do you understand an event with 1,000 particles coming out of collision? And so a basic thing you could ask is, well, in physics we learn to ask, are there jets? Where are the jets? Where are the most high energy initial particles that came out and then decayed into one of these jets or clouds of particles? And you'd like a systematic way of partitioning the space of events into these 2-jet, 3-jet, and so forth events. And there are many tools, handcrafted statistics for data analysis invented for that. But you can also try a general approach, and that's what this reference here does. You just take the distribution of energy coming out of the cylinder, a 2-dimensional cylinder that you imagine surrounding the event. So I was giving you some function from the cylinder to numbers, energy coming out there. And now you can use this Wasserstein distance, which is saying, given 2 probability distributions, what's the minimal move of probability from each point of one to each point of the other, and then weighted by the distance to some power, in the simplest case just the distance. So I try to minimize this overall ways of moving stuff. If it's 1 here, so you'll call this the earth mover's distance. The big pile of dirt, what's the most efficient way to move it over there? And then just applied to this energy distribution, you reproduce some of the standard measures that allow you to basically cluster and identify jets. So interesting way to solve a specific problem in this general framework that many fields can adopt. Okay, pure mathematicians, again, from the outside, it seems to me there's much more of an interest and willingness to look at probabilistic models, even in number theory, the least probabilistic of subjects. And this is not, again, a new idea. So you could say that the basic probabilistic model of a prime number is that the number's got half a chance of being even, a third of a chance of being divisible by 3, a fifth of a chance of being divisible by 5, and so forth. And then you can start correcting for the obvious correlation between those things. But then you can get into more and more sophisticated such models. Just as an example, I won't go into details, but a collaboration from 2013, Manjul Bhargava and collaborators gave a probabilistic model of the ranks of elliptic curves. So this is a description of the space of solutions to a cubic equation of this sort in rational numbers. Okay, so sometimes they have no solutions, sometimes finitely many. When they have infinitely many, there can be some set of generators. Okay, and that's the rank. It's the number, if you can generate it with the r+1 things by using a sort of addition law of elliptic curves, then the curve is of rank r. And there is, I believe, 36 now. I just heard Module Bagala talk, and a little bit more is known. There is a curve of rank 36 known, and the general belief now, based on these models, is that there is a limit. There is a maximal rank beyond which there will only be finitely many such curves. And again, it's not a proof, but it's this probabilistic way of thinking, which I think is also, it ties in with some of my other topics, but it is a trend in the mathematical sciences. Okay, so let's switch now to another and arguably, the most important topic. To different mathematicians. None of us will be doing mathematics in the year 2130, but our students will be doing it. And so what would a math textbook look like in 2030? And well, we have used textbooks to teach our classes. We've learned from textbooks. We have an idea. And of course, a lot of the design choices were made based on the medium. It's true, the length of the textbook is adapted to the length of the course that we might teach, but the physical layout, the linearity of the textbook is much more because of book technology. And we haven't even exploited the fact that usually people read it on a screen now. And so there's many possibilities to be explored, even just talking about textbooks. And I'll just throw out, ideas, which the technology really exists, but again, it's hard enough to use it that I don't think people have tried to evaluate a lot or combine these possibilities, right? So you can easily imagine a textbook where you maximize the possibility of links, you maximize the possibility of suppressing unwanted information until the reader, the student, clicks on something. Ideally, of course, you would have automated grading of exercises, and of course, we would all love that. My daughter's taking computer science courses as an undergrad, and I must say this, even in that field where it's the best case, there are many challenges. Social learning, these Q&A sites, so people exchange hints, answers, ideas about problems, and that's going to happen, whatever, you may think it's bad or good, but definitely going to do it. And one should try to work with it, it's a resource, it's something that students can benefit from. You can imagine, again, if you try to brainstorm, there are many possibilities for how the textbook of 2030 could be different than it is today. Okay, and then to get into this now, not just media aspect, but the computational aspect, there are many textbooks on computational science, computational physics, mathematics, and the like, but they tend to be they assume that you know the subject and they're based on some particular system. We're going to do this class of problems in mathematics. We're going to talk about these particular methods. And one can imagine that it would be better to integrate the discussion, to use the computer in the teaching of the concepts, and to enable the student to think, computationally, but a bit more abstractly, not just in terms of a given system. And so, if the slides are up, I'll let you go through this and perhaps not belabor the point and just give an example of what I think is an interesting effort. And this is already like 15 years old, this textbook. This is Sussman and Wisdom, Structure and Interpretation of Classical Mechanics. So this is a famous computer science professor and planetary scientist at MIT collaborated to make this Introduction to Classical Mechanics, a very sophisticated one that gets into even Hamiltonian perturbation theory and celestial mechanics, as well as topics of chaos and the like, but does it in this computational way, and not just in terms of here's an example that you can run and see what the phase space and the orbits look like, but even the formal, the computational, the definition, how you go from a Lagrange to Hamiltonian, it's all done with computer examples. So it's a very interesting illustration of what you can do in that direction. Again, just with the existing technology. Okay, so now let me do the interactive theorem verification. And so this again is actually an old topic, this idea that computers should be able to prove theorems, and as such it's received a lot of attention in computer science, both in terms of math, but the real core of this field is proving that a computer program is correct. So you have some statement, specification of what the program is supposed to do, and you'd like to prove, yes, my program does that. And there are cases clearly where that would be of incalculable value. So like an airplane autopilot. If you could prove, yes, the autopilot within this wide range of circumstances will always do a reasonable thing. Another famous example is CPU floating point unit. So there was this famous mistake that Intel made in the early 90s, I think, with the floating point unit. This was soon after the IEEE floating point standard was established. And they misimplemented a few cases. And in the end, it was just so much trouble to convince people there are just a few cases that they wound up recalling all their chips, and it cost them more than $1 billion. And ever since, they formally verified their floating point units, and then the rest of their chip. And so there are cases where it's not easy to do this, to prove that a program's right, but it's worth the expense. Okay, so just to, again, not be abstract, but to give a little example, I'm afraid I may start running out of time, so I can skip more quickly if I get the indication, but let's just go through this. So this is an example of how you would say my program sorts a list, say, of numbers. And this is written in the system Coq, which was developed in France. And it's actually fairly, I don't know if everybody can read it, but it's fairly clear. It says that a sorting algorithm is something where, given a list, the new list is a permutation of the old list, and the new list is sorted. And sorted is pretty obvious. The elements that appear earlier in the order are less than the elements that appear later, less than or equal. And permutation also has this kind of pretty recursive definition that no list is a permutation of itself. If you append an item to the front of of two permutations, it's still a permutation. If you attend the transposition and repair, then that's a permutation, and it's transitive, and then you prove that that generates permutations. And then there are, it's not that hard, and this is textbook material, to prove that one of the sorting algorithms you would learn in undergraduate course, like quicksort, which is kind of intricate, does sort according to this. So that's like the core of the subject. But now, is this of use for mathematicians and theoretical physicists and such people that would be happy to prove that their results or verify their proofs if they can do it? So just to give a concrete example again, we all know the fundamental theorem of algebra. We have a complex polynomial, degree greater than 0. It has at least one root. Okay, and then this is a logical statement, and this is now the system called a mean. And it's a fairly clear, concise statement of what we just said. And I won't go through it, but this is an outline of the informal, the standard proof of this. Okay, and if you spell out all the details, it might be 2 pages long. So here's the first part, the first paragraph 1, bullet 1, translated into this mean. Okay, so exists for all. So it's saying that there exists some x such that for all y, and given the polynomial p, the value of the absolute value of p is a minimum. Okay, and then this is over all the complex numbers. So the polynomial attains its minimal value. And of course, you need some topology to show such a statement. And then you read this, and the basic situation is that the statements of the theorems actually are pretty clear, and then the details that you need to prove them are really not very clear, and include all sorts of weird, long definition names. These things like simp and RW, these are what are called tactics. So they're saying, like, I have to use this axiom and rewrite my proof at this point. Now here I can bring in some kind of general algebraic simplifier and make my life simpler. But it's not an easy thing either to read or write. And there's a variety of reasons for this. And in my mind, one of the key ones is to seem to name so many intermediate results. And you have to remember the name, you have to remember how you use them, and so forth. Okay, so it works. You can, at this point, they've gotten to the point where very strong mathematicians feel that, yes, you could formulate any mathematics, any principle, make verifiable proofs of it, which is not to be taken for granted, or even as a relatively recent development, but hard to actually make those rigorous theorems. Okay, so I and obviously people work on this, but even me, not a mathematician, feel that this is a central thing in the relation between computers and mathematics. And there's a variety of reasons for that. And maybe the most simple one is to say that to try to get the computer to understand anything is very difficult. Usually it's calculating, it's not understanding anything. And here is some, at least, lever of understanding. It sees that the thing is true and it can prove it, right? You can debate whether that's understanding, but that is a central part of math, for sure. And so to get it to be precisely represented in the computer has to be a central aspect of the discussion, but it's still hard to use. So what do we do? Okay, so I commented that the definitions are easier to write than the proofs. Okay, we might focus on definitions. It might be that deductive logic is not the be-all and end-all, even though that it is for these systems, but maybe we need to be broader. I don't have time to really go into that. Finally, maybe machine learning and AI will make these systems look better. Okay, so to talk about that first, now there's a mathematician, Tom Hales in Pittsburgh, who has verified one of his own. If I have time, I'll come back to this Kepler conjecture that he proved and formally verified. So probably the pure mathematician with the most expertise in this. And he has a project that he calls Formal Abstracts, which is basically to make a repository that, like the archiving principle, that you can upload a formal, precise statement in the style that I described, even in that language lean, of what you've, something you proved in your paper, and it will be there for the computer to search, for people to look at. The computer may not be able to prove it by itself now, but it could be, in principle, prove it. And some discussions. There'd be a long library to make it possible to do that at research level, but not an infinite library, 50,000 definitions or so. Something that could be done within a few years. And part of he's working on now is that you can actually simplify this kind of computery language. So this is a controlled natural language. This is a language that looks like English and standard mathematics, but can actually be parsed by the computer into the form that I described before. So this is group theoretical silo theorems in a fairly readable and hopefully writable way. So that's an interesting development. Let me say a little bit about, I'm not going to actually go into much this existing proofs. An interesting example for physicists is this G minus 2 of the muon. Okay, let me just spend a minute on this. Okay, so this is a very important measurable to about a part in a billion, even better, that will allow us to detect new physics. And last I heard, actually the theoretical prediction and the experimental number differ by not quite 5 standard deviations. But back in the late 90s, there was also a 3 sigma disagreement between this theoretical calculation and the experimental measurement at that time. It turned out to be a mistake. Okay, it turned out to be kind of an embarrassing mistake because you had to combine results from various different calculations. And one of the calculations, the symbolic algebra system they used, they didn't quite get the conventions right, and they added that contribution with the wrong sign. And that was where that came from. So that's one of the cases where this kind of verification really would have helped a group of physicists. Okay, so let me spend a few minutes on this topic of AI and theorem proving and not try to delay the party. Try not to delay the party. So, okay. So another answer to this question, maybe the computer could help us prove theorems or even prove its own theorems if we could just apply AI to it. And there's a strong analogy between what it's doing in this theorem proving and a game of solitaire. You have moves. You have to choose, which statement do I draw to add to the proof to make a deduction from, which law of logical inference or rewriting do I use. And so I have these choices, just like the moves in a game. And as we know, AI has been staggeringly successful at certain games, with the famous example being the AlphaGo. And so there are groups that are using basically the same approach to get these theorem provers to learn to prove theorems at Google, at Princeton, and various other places. And the strategy is to take the existing proofs that people have written for these systems as a training set and let the computer learn how to prove from that. And they've actually gotten up to like a 50% rate of little like few line proofs that the computer can then automatically prove once it's learned that. And that's the limiting point at that point. Not that much math has been encoded that way. Other people are thinking about this question, well, what if the computer could read the archive? Could we translate mathematical papers that people write into this kind of formal logic or something. I mean, there's very interesting questions that come out of that. The AlphaGo, of course, there are many keys to its success, but one important thing about playing a game is that there's no shortage of data. The computer can play itself and just produce arbitrary amounts of data. And of course, mathematics has that property too. A good mathematician could fill up pages and pages, and it could never stop. And why can't the computer just generate its own training data? And of course, the answer is that, well, in a game, it's competitive, and you know when you win. The computer keeps getting better at playing its previous incarnation. But in mathematics, just generating logical statements is really not mathematics. You have to generate interesting statements. And what is interesting? Well, that's a very deep question, but one that I think one can give candidate answers to in this type of framework. Objective functions that talk about statements being interesting because they can be used to prove other statements, or because they come up in many other contexts. So this is, again, one of these old things that people have tried over the years, but that I think will be an important thing to come back to. Okay, so if questions about that will all be at the party, but let me just briefly summarize. So these were some of the more kind of straightforward things that I went through. But now let me speculate a bit about what this could add up to by 2030. So I really do think that there's a great opportunity to write better textbooks for the mathematical sciences that both use even the technologies that we have now and integrate computation in a better way. And I predict that most textbooks we have now will look kind of dated by 2030, and there really will be so much better ones. Okay, the computational mathematics will continue to make significant discoveries, but of this kind of intricate character, potentially important results where it just was a intricate but finite way of just computing the answer to the problem. That's a valuable thing. These theorem verifiers will be much easier to use. So I would venture to predict that the computer won't be proving things by itself, but that these systems will be as easy to use as Mathematica is now. Okay, to say that if you are a mathematician who really wants to verify the theorem that you're about to publish, that you won't have to spend a year learning how to use the system. You'll read a book and you'll spend a few weeks checking out your theorem, and it will check. So that will make a big difference to many fields. I don't have time to discuss how a physicist would use that, except for perhaps getting out of these bugs like the G-2, but I think it will be equally important for us. And this mathematical search will exist and be another standard tool, and that one will find search results which really teach us non-trivial things. That you search for X, you thought X was a concept defined in some field, but it turns out that there's Y in some other field, which is actually like 2 steps beyond X, and it's much better. And now you've connected these 2 fields, but it's because your search result has taught you something. And no doubt there are things like that that have happened in the past, but a discovery based on this kind of semantic search would be a very interesting thing. Okay, so then finally, as this kind of ultimate question, will computers start to do their own mathematics? Will computers have proven any major result without just being the tools of the humans trying to prove it? And I have actually I don't know. Here's what how I will answer that question. Okay, so we cannot guess because we do not have the ingredients right now. So, okay, I would say that computers, and I think this is uncontroversial, cannot really do reasoning in a general context. Obviously, they do all these kind of special forms of reasoning where the problems are already interpreted and parsed into some form of framework. But general reasoning, asking Siri or Alexa, a general, even a one-sentence, fairly general question relying on common knowledge is far beyond where they're at now. But maybe not far. Nobody really knows that. That's the kind of topic that people work on intensively. But it's not there now, general reasoning. I don't think mathematical or physical general reasoning is easier than general reasoning. It's unclear whether it's harder, but I certainly don't think it's easier. Okay, and in fact, other domains certainly will receive much more attention from industrial labs and researchers than pure mathematical reasoning, and they have various advantages. But the big advantage of math, of course, is that it is not quite pure reasoning, but it's the domain that depends the most on reasoning, right? So if you're a lawyer and you make a deduction, you then anticipate something that your opponent might do, you make another deduction, you made 3 steps, then you might as well go home for today. That's 3 steps, in these human endeavors. That's already about as far as you can predict. But in math, of course, you can write a book that chains together thousands, tens of thousands of statements, and it can have meaning. So once the computer has any ability to do this general reasoning step by step, math is a place where the computer's ability to put the steps together sequentially and get them all right will really pay off. And then we could try to guess that this then becomes not a purely technological problem, but a problem that becomes more like problems that have been solved. So if you look back at the history of computer Go, the breakthrough that led to a lot of focus was Monte Carlo tree search, which was made around 2006, and it took about 10 years before AlphaGo. And so we might guess that 10 years after this kind of general reasoning ability shows, the computers show some ability to do this, that we will start to see serious ability of computers to do their own, general mathematical reasoning. So I'll leave you with that thought, and thanks for your attention.
Questions for Michael?
So I was curious about what your thoughts were on going back to the math search engines. I think it's remarkable that they're able to sort of do all of that, but I wonder what role they might have to play in the process of democratizing mathematics to people who may not necessarily be able to formally put together these
that's right. I think
statements.
that's another opportunity that I didn't emphasize, but that's right. I think a lot of it's another general philosophy I always have, is that many times the effects of this type of technology are not as much to extend the capabilities of the expert as to democratize them, to make it available to a much larger audience.
Yeah.
That's right, and I think that's a very important point.
It's very exciting.
Yeah.
Thank you.
I have actually 2 questions.
Yeah.
One is, you mentioned briefly the difference between interesting statements and non-interesting statements.
Right.
Indeed, the statement 2 + 2 = 4 to me seems not interesting, although I heard that it's difficult to prove. While the statement that zeta function has zeros on some stupid line seems to be strange to me, but I heard that it's interesting. So is it possible to do some criteria to formalize, maybe to do artificial learning?
I think it's an important problem that
find-
hasn't received the attention it deserves. And I think it would have just been kind of philosophy until recently that would be new, you could deal with a precise answer. And now we could imagine trying out a precise answer in some systems. So I think it's very interesting and deserves to be discussed at the party.
Okay. Then I can suggest another question to discuss at the party. Your title is How Will We Do Mathematics in 2030?
Right.
I suggest to cut one word from it. Will we do mathematics in 2030?
Yes, that's another talk. Also important.
Actually, I had a question for you.
Yeah.
So you gave this example of this mathematician in Pittsburgh who's developing
Right.
this,
Tom Hanks.
so readable form.
Right.
And you mentioned something under your breath about easily writable.
Right.
But the Achilles heel, or one of the major problems for just about any programming language or
Yeah.
symbolic algebra program is, misplaced semicolon completely
Yeah,
destroys
that's
it.
right. That's
So-
right. That's and then that's right. In his language, it has to get translated into this not just syntactically but semantically somewhat rigorous and constrained framework. So it's an open question, and indeed you can wonder. But his project is ambitious. I think it is one of the things that could be done in the relative, the next 5 years, like I said, but it may be that it becomes, because of what you said, that's the type of point he's trying to explore now. Yeah.
So just going back to the first question, to a certain extent, I guess the whole model of teaching in universities is kind of almost dates back to the Middle Ages, which Philippe mentioned in the book, because you didn't have printed books, so somebody had to sit at the front and lecture, meaning literally read a manuscript that was just this one copy of, right? So a bit like the archive almost, or before the archive. But
Right.
so these developments in terms of, books which are non-linear, in terms of information being available on the internet,
Right.
and not just in in various forms you've discussed, but even in the basic form of a YouTube video
Right.
by a particular, somebody who's an expert in the field. What are the implications of these kind of developments for sort of the business model of universities as institutes of higher education?
Well, that's a very good question. I mean, we'd have to, I think, step back even more, from any details at this level. And that's right. I mean, maybe that's, let's say, I don't think I have any crisp, immediate thoughts to give you about that. Though it's clearly an important question.
So, like, part of mathematics is also to create concepts and create words, literally.
Yeah. Right.
Functors,
Right.
morphisms,
Right.
the words that you create depend on the school, on the country. So, has something been created, has some concept or mathematical structure and attached word been created already by?
I'm pretty sure the answer would be no,
Automated.
because I think the question presupposes that the creator understood what they created. So the answer would have to be no.
Also about this topic about understanding, if I have something that automatically solves something for me, that proves some theorem,
Yeah.
then I presume there might be different ways of doing this proof.
Right.
Is there some way of now telling the system, please give me a proof that is easy, that I might have sense of understanding, instead of generating 200 terabytes of output? Is there some way of going in a
Yeah,
direction
yeah.
where
In
you
the
learn
SAT
from
context, definitely yes. They do work on that. That's right. If can you simplify? Is it definitely yes. In that SAT context, where again, I mean, in this other context, the interactive nature is to say that people, it's not automatic. People collaborate with the computer in a sense, or use the computer as a tool. But in the SAT where it's automatic, definitely yes. That kind of thing exists.
So you talked about taking papers from the archive and converting them to formally true papers.
Right.
Not all papers
Not
on the
necessarily
archive.
formally true, but at least formally stated.
Right. So not all papers are formally true,
Right. Right.
at all.
Right.
So what possibilities do you see for finding inaccuracies or errors?
Well, that's another very interesting question. I mean, yeah. I knew I wouldn't have time for it. I have more slides about exactly this aspect of the steps of turning something informal into formal. And so to the extent you can do that, obviously, that becomes a real possibility. But I think there are several steps. I think it's optimistic to think that even 10 years from now we'll be able to correctly turn. We will turn these documents into something which is written using the formal symbols, but this part won't be coherent with that part, won't be coherent with that part. So it'll be a step, but not enough to answer your question in generality.
Let me ask one more question. It's really about AI more generally, I guess. But so oracles are useful for sure. People have looked for oracles for a long time, as long as they tell you the truth. But their utility is limited because, at least as scientists, what we really care about is understanding more than answers to specific questions. So if these, automated proof finders or problem solvers start spitting out, masses of new results, but we don't understand how they're getting them, and we can't really follow the proofs.
Well, these are not getting into the deepest questions. That's right. So, of course, the nightmare is that you get out this million-page proof of the Riemann hypothesis, but it has no structure, and nobody can figure it out at all. And then the other, the most positive version of it, to say, is something like the ability to do arithmetic to kind of calculate or symbolic manipulation on Mathematica that frees you to look at a higher level. And so you're really understanding more, and any given piece that you're neglecting at the moment, you could zoom in on if you want, but you don't need to normally. So there are these two extremes, and obviously it's to us to make the tools useful for us.
One more question.
Yeah, sure. So I was just on a lower level, how do you see the way that we'll interact with computers and each other with computers change in the next 10 years? Will we still be using keyboard and mouse to put all these things in? And is that the most efficient way?
That's a good question. I mean, again, I don't think the breakthroughs are going to come in this area. They're going to come in more consumer or more other domains. I mean, obviously, I mean, people are working hard on dialogue. Then it's like if you ask you what is the single most valuable problem that would bring the most immediate financial rewards, is dialogue. Even in kind of very constrained domains. So I would guess, within 10 years, we will certainly be having dialogues with computers in restricted domains like buying airplane tickets or things like that, and possibly quite a bit more than that. And probably not math, I would think. Although, again, if you broaden this concept of dialogue, but we won't be talking to the computer as if it were our colleague in 10 years about mathematics.
Okay, so I was careful to take pictures of your prediction slides so that at the holiday party in 2030 I can harass you. For now, thank you very much for the talk. And,